An electric vehicle at highway speed? Battery climbing not draining, no plug, no stop, no downtime. Electric roads that charge cars while they drive sound like a concept render. But in Detroit, Tel Aviv, and on a French motorway, this is already real. The technology works. So why isn't it everywhere? The answer starts with a problem that even the fastest chargers on Earth still can't fix. To fully transition to electric transport, fleets must overcome two massive hurdles: range anxiety and charging downtime. Right now, even the fastest commercial direct current chargers require 20 to 45 minutes to deliver a useful charge. For passenger cars, that is a minor delay. For commercial vehicle fleets, it is a major financial loss. Simply building more plug-in stations cannot solve the math of a stationary vehicle. When a city bus, a delivery van, or a heavy-duty freight truck sits idle at a plug, it is not moving cargo and it is losing money. These transit and logistics operators feel the pain of charging downtime most sharply because their businesses rely on keeping wheels turning. Trying to bypass these stops by installing larger, heavier battery packs only penalizes the vehicle, reducing payload capacity and increasing overall energy consumption. In-motion wireless power transfer offers an elegant answer, feeding electricity directly to vehicles as they travel. By converting the road itself into a continuous power source, batteries can shrink and vehicles can run indefinitely. Yet shifting high-voltage power from a fixed plug into the asphalt beneath a moving lane solves one crisis only to introduce a complex web of engineering challenges. The physics behind this concept rely on principles of electromagnetism discovered in the 19th century. The dominant approach is inductive charging, which functions like a massive version of a wireless smartphone charging pad. Flat rectangular copper coils are embedded a few centimeters beneath the asphalt and connected to the electrical grid. When an alternating current passes through these road coils at a resonant frequency, typically between 85 and 100 kHz, it generates an oscillating magnetic field. As an electric vehicle equipped with a matching receiver plate passes overhead, this magnetic field induces an electrical current in the vehicle's secondary coil. The onboard system rectifies this current, converting it into high-voltage direct current that feeds directly into the electric motor or battery pack. This wireless transfer occurs across an air gap of 10 to 15 millimeters, completely shielded from weather by the protective layer of asphalt. A competing approach bypasses magnetic fields in favor of direct conduction. Instead of buried copper coils, conductive systems like those developed by Swedish firm Elways embed a metallic power rail flush with the road surface. Vehicles using this system are equipped with a physical, movable pickup arm mounted beneath the chassis. When the vehicle enters the charging lane, this arm lowers to make physical contact with the rail, transferring electricity directly to the vehicle. This connection eliminates the magnetic coupling losses inherent in inductive systems, allowing the conductive rail to deliver up to 200 kilowatts of continuous power directly to a moving heavy truck. While inductive charging offers a sealed, non-contact solution, conductive systems trade that simplicity for the high efficiency of direct physical contact. Both methods turn the roadway into a power source, but they require entirely different hardware under the pavement and on the vehicle chassis. Bridging the gap between a vehicle and the road requires solving a massive system integration puzzle. First is the challenge of physical alignment. For an inductive system to transfer energy efficiently, the vehicle's receiver must line up precisely with the buried road coils. At highway speeds, even a minor drift out of the lane center degrades power transfer, turning electricity into wasted heat. Then comes safety and control. A charging road cannot remain constantly energized. Doing so would create an active safety hazard. Instead, the road relies on segmented activation. The system must detect a vehicle, perform a split-second communication handshake to verify its identity, and turn on only the specific coil directly beneath the chassis. As the vehicle moves, the previous segment must shut off within milliseconds, while the next one fires up. This makes dynamic charging a software control problem as much as a hardware challenge, requiring encrypted data transfer to handle authorization and billing on the fly. Because of this complexity, the early business case belongs to commercial fleets rather than passenger cars. City buses, delivery vans, and heavy trucks travel predictable, high-utilization routes. Equipping these fleets with in-motion charging shrinks their battery packs, slashes overall vehicle weight, and maximizes operational uptime by completely eliminating charging stops. In Tel Aviv, Dan Public Transportation operates a transit bus over an electrified 700-meter section of road near Tel Aviv University. This municipal corridor, developed with the local transit authority and tech firm Electrion, routinely charges active buses during their daily routes. Across the Atlantic, Detroit's 14th Street hosts the first public wireless charging lane in the United States. Through a partnership between the Michigan Department of Transportation, Ford, and DTE Energy, a retrofitted Ford E-Transit shuttle continuously tops up its battery while driving over a quarter mile of pavement. In France, the A10 motorway features a high-speed dynamic test lane managed by highway operator Vinci. Here, heavy-duty freight trucks traveling at 90 kilometers per hour draw an average of over 200 kilowatts of power directly from the roadway, hitting peaks of 300 kilowatts. At commercial shipping ports, InductEV deploys specialized wireless pads to keep high-use terminal tractors running without plugs, while Ytricity's Halo system provides car manufacturers with a direct, factory-installed option for consumer passenger vehicles. These deployments show that dynamic charging is already functional across municipal streets, interstate highways, freight hubs, and vehicle platforms. In December 2024, the Swedish Transport Administration released a final report that ground national ambitions to a halt. The agency recommended against building a national electric road network, prompting the government to pause its planned rollout. The primary obstacle was the cost of installation, estimated at 24 to 29 million Swedish kroner per 2 lane kilometers. Beyond the immense capital expense, a massive compatibility gap remains. The vast majority of electric vehicles on the road today lack the specialized receivers required to draw power from these systems. At the same time, global manufacturers have yet to agree on unified technical standards, leaving operators wary of investing in hardware that could quickly become obsolete. Under heavy freight traffic, long-term pavement durability and coil maintenance also remain untested risks. These constraints mean that the viable near-term case for dynamic charging is limited to fixed-route commercial fleets. Building a cost-effective, high-speed charging network for everyday passenger cars on national highways is still a decade or more away. The path forward begins not with passenger cars, but with heavy commercial fleets. Transit buses, delivery vans, and heavy freight trucks running fixed, high-use routes represent the realistic first wave of adoption. From there, the medium-term opportunity lies in electrifying highly targeted, high-traffic highway corridors rather than entire networks. In the long term, this infrastructure could allow passenger electric vehicles to carry much smaller, lighter batteries, topping up on the go to drastically cut vehicle weight and manufacturing costs. Sweden's ambition to equip 3,000 kilometers of road by 2035 remains a guiding target for this transition, while the European Union's standardization process establishes the rules for eventual scaling. If the technology achieves this scale, would you be willing to pay a higher road toll to charge your car while driving? Subscribe for more technical breakdowns. The future of electric roads isn't a challenge of physics, but of finance. As infrastructure ages, the real barrier is who pays for the upgrade. Would you pay a premium toll to never plug in again? Subscribe for more engineering insights